In this video, we will talk about the curl of a vector field. So curl means the circulation of a certain vector field around a point. So first, for example, if we have a vector field like this, curl informs us how much this vector field curls around a point. So let's look at how to compute the curl. Computation of curl. Curl can be computed by taking the cross product between this Nabla operator and our vector field. So we know our Nabla looks like dabba dabba xi, dabba dabba j, and dabba dabba zk in the Cartesian coordinate system. And if our vector field f is also something like fxi plus fyj plus fzk, then the curl of f can be calculated by taking this determinant, which is written as jk. This is our first vector, x, z. This is the second vector, x, fy, and fz. So when we are taking the determinant, if we want to calculate the ith component of the determinant, we will take these two terms. So then that will be the ith term will be dabba dabba z minus z fy, and for the jth component I will write here minus j, and I will take these two terms. So that is going to be dabba dabba x fz minus dabba dabba z fx. And for the kth component, you take these two terms here. So it will be plus k dabba dabba x fy minus dabba dabba y fx. So that is how you would calculate the curl of a vector field. Now we will look at the physical significance of how do we show that Nabla cross F actually gives the curl or the circulation of the vector field. So let's consider a two-dimensional vector field in two dimensions. So let's say my vector field goes like this on this plane, and I want to calculate, this can be written as fxi plus fyj, and I want to calculate the circulation. So in this example, I will select a small loop, small rectangular loop to calculate the circulation. The circulation means actually the line integral of my vector field along this loop. So line integral along this path, let me call it 1, plus the line integral along this path, let me call it 2, along plus the line integral along path 3, plus the line integral of the vector field along path 4. Therefore, the circulation I can write as circulation of the vector field can be written as 1 in path 1 f dot dl is the line integral or the path length, f dot dl, part 3, f dot dl, part 4, f dot dl. So let me calculate these line integrals along different paths separately. So let me take the path 1 first. We take the line integral of this vector field along path 1. So path 1, if you look at, it lies only along the x direction and there is no y contribution. Therefore, the line integral of our vector field along the first path would only be the integral of our vector field, the x component of our vector field times the length of the path. So this will be the line integral along path 1. Let me then take the line integral along path 4, which goes down. So along path 4, we can see there is no x component, so only we are integrating the y component of the vector field along this path. So in that case, we have along path 4, what we have is along path 4 f dot dl will be our y component of our vector field times dy. However, in this case, dy will be minus because when we are adding the line integrals of these different paths in the anti-clockwise direction, this will be negative dy. This arrow goes in the negative y direction. Therefore, we have minus dy here. So when you look at path 2, now path 2 also changes only in the y direction. Therefore, we will be integrating only the y component of the vector field. However, we can think of this path integral as the line integral of path 4 plus how much our vector field, y component of the vector field changes with respect to x. Therefore, that expression, so the line integral along path 2 of this vector field, we can write it as, it will only be the y component that is changing along that path if y plus how much our y component of the vector field changes with respect to x, that is given by dA by y dA by x, and times how much our x has changed. So this is the change in field or the field y component of the field where our path 2 is, can be written like that, and the line integral, to take line integral along path 2, I have to multiply this by d1. And then similarly we can write down the line integral of the vector field along path 3. We can consider it as the line integral along path 1 but shifted to 3 so that the x component of our field has changed with respect to y. So I can similarly write the line integral along path 3 f dot dl can be written as fx and how much fx changed with respect to y times how much y has changed, how much our y changed times the length of the path. Now the length of the path will be dx. However, using the sign convention, it will be minus dx because these two arrows are pointing in different directions. So we have taken this direction as plus dx and this direction has to be minus dx. Now we can adapt all these four components. So along path 1, it is going to be fx dx. Along path 2, it is going to be fy dy plus dabba fy dabba x dx dy. And along path 3, it is going to be minus fx dx minus dabba fx dabba y dy dx, and along path 4 it is going to be minus fy dy. So we can see that these terms will cancel out with each other, and what remains here is these two components, which we can write as fx dabba y times dx dy. And if you look at this component here, you can see this is the kth component of the curl of f. So this indeed is the kth component of the curl of f. Therefore, the circulation is curl times the area. Therefore, we can define the curl as circulation, which can also be written as line integral of the vector field along this closed loop that we are considering, and the area. So this is actually how you can define the curl. This is the definition of the curl, where we talked about computation of the curl earlier. So by calculating the curl, you can get information about how much your vector field circulates around a given point.